when we want to determine continuity of specific functions or the intervals of continuity of specific functions, the best thing to do is to take each component and figure out on what interval each one is continuous, and the intersection of all the intervals of continuity is the actual total interval of continuity. Think of it like a weakest link principle. You have to take the smallest subset for which they all overlap. So I'll give you an example. So let's take a look at this function. So if I think of like a number line here, and this is 0, what I do is I take a look at this function, 1 over 2t plus 1. And I say, all right, what values can't go in there, right? When we think about continuity, it's much, much easier to think about values that it's discontinuous at than the values that it is continuous at. So if you think about the graph of 1 over 2t plus 1, it is that this thing works fine for any value you plug into it, except right where it blows up, right? Where t equals -1/2. If you think about t equals -1/2, that's going to be a -1 plus 1 is 0, blows up. So right at that -1/2 mark, you have a problem. But every other value is fine. Okay? So then we look at 1 over t. Well, 1 over t is fine everywhere except for t equals 0. So then it blows up there. So what we do is we put these together, and we take, again, we take those holes from each one of them, and what's left over is your final result. So if I put those two together, I get this. So this is the interval from -infinity to -1/2. Remember, it's open because we don't include that. And then that intermediate piece, we union that in. So that's -1/2 to 0. And then we take this piece, which is 0 to infinity. So your interval of continuity, your intervals of continuity are all three of those. Now, if we take a look at this particular piece, we can do the same idea. So this is just the function t. So think about like f of t equals t or y equals x. That's just that straight line through. That's a perfectly continuous function. So the whole interval is fine there. So we don't even need to draw the purple line. We could. Now for arc sine. Now if you remember about the arc sine or the inverse sine, if I take a number and I put it into the sine function, what I get out is something between -1 and 1, right? Think about the sine wave. It comes out between -1 and 1. So the outputs of the sine function are -1 and 1. So the inputs of the arc sine function are -1 to 1. That's how they're related. So anything outside of that, it's not possible. And so that, I mean, I know that we're discussing really domain more than we are continuity. So what we're going to do is that one goes from -1 to 1. But it includes those values because they are continuous from the left and right hand limits. And finally, we have t minus 1 here, which is a lot like t. If t's here, t minus 1 is here. They're both just lines. And so it's continuous everywhere. So really, this was the only value that limited us. So your interval of continuity is -1 to 1. Now finally, we have this. Now this is a constant function. So it's continuous everywhere, right? It's just a flat line, continuous. Square root of t. Well, that's that function. And so it's continuous along the positive. It's continuous along the positive x-axis, or the positive t-axis, but it's not continuous anywhere else. Now, if you remember what the cube root of t looks like, that looks like that. Cube root of t is continuous everywhere. So, since it's continuous everywhere, then it would overlay here. But again, we take that weakest link principle, so we take the intersection of those two. And so our interval of continuity is 0, infinity. And that's how you do it.